construction of finite automata. Automata can remember the information on behalf of transiting the states. How much information actually your automata need to remember, or what are the strings in the set for which it should go to one place, and for other string it should go to the different states. So we are going to see in this class. So we are going to identifying the strings which are distinct. How we can say one string can be distinguished with respect to your language. So we assume that we have the language L, and the L is what? L is the subset of the sigma star. So why your automaton goes one place for some string, and for some other string it goes to the different places? What is the reason behind that? So here we will see that actually these strings are distinguishable. If your strings are distinguishable, then your FA must go to the different places. So we have the language L. If you say that X and Y, which are taken from the sigma star, X and Y are distinguishable with respect to the language L, then what you need? Then there is a string Z which belongs to sigma star such that exactly one of the strings, which one? X, Z and YZ is in L. So this is the condition. If you say that X and Y are distinguishable, how would you say that X and Y are distinguishable? So for that actually you need some string Z. This Z may depend on the string X and Y also, and Z can be anything. Z can be null string also. There is no issue. You need to, if you say that X and Y are distinct string, and means X and Y are, your FA should distinguish the string X and Y, then you must have some string A, Z, there must be some Z. You may have some string Z which is taken from the sigma star such that exactly one of the strings XZ and YZ is in L. This means you have some string, you have X and other string is Y. If you say that X and Y are distinguishable, then what you are doing? You are taking some string Z which is from the sigma star, and you are concatenating with X and Y. So you have the string XZ. So if X and Y are distinguishable, then on receiving the string XZ, this string may be in the language. If this is in the language, if this belongs to the language, then YZ must not belong to the language. This is one condition. Or if XZ does not belong to the language, then YZ must belongs to the language. So that's why I'm saying that exactly one of the strings XZ and YZ is in L. So either XZ will be in L, or you may have the YZ in the L. If XZ is in L, then YZ will not be in the L. If XZ is not in L, then YZ will be in. If this is the condition, then you can say that the string X and Y are, you are going to distinguish, your automaton should distinguish these two strings X and Y. Means X and Y are distinguishable with respect to the string Z. So what is the significance of this? Actually, why you are saying like this? If X and Y are distinguishable, if it is distinguishable, then what happens? Your FA must go to the different places. If X and Y are distinguished, if you say that your FA should distinguish the two string X and Y, then on receiving the string X and Y, your FA must go to the different states. And see, starting from the initial state on receiving the input x, you have your fa may start from the initial state, we assume that, and you may have some string x. On consumption of the string x, it is going to the state, say for example q. Okay, there are some there is some state q which, so on receiving the string x from the initial state 0 q0, your fa goes to the state q, and for the other input, say you have the y, on receiving the string y, your fa goes to the different place, say for example q dash. So and from z, if you submit some string z, and if you are here and if you are going to string z, then your fa goes to some state, say for example it may go to the states like this q double dash. Okay, and this may go to the states q triple dash. So what we mean that if x and y are distinguishable, then on concatenating z, your fa goes to some state. So if either this state is final or this state is final. So if this state is final, then this must not be the final state. So this is the condition. So exactly one of the strings is in L. If this is the final state, then xz will be in the L. If this is the final state, then yz will be in the L. So this is the condition. If if your fa goes to the different place, it means x and y are, if x and y are distinguishable, then your fa must go to the different places. If your fa is not going to different place, this means you don't want to distinguish the strings, your fa don't want to distinguish the string x and y. So that's why you need to know that which of the strings in your sigma star your fa need to distinguish, and the strings for which your fa is going to distinguish, for such strings your fa must go to the different places. So if you have the two strings x and y, you have two string x and y from the sigma star, and you can take some string z from the sigma star, and on concatenation of xz and yz, if you have the condition xz is in L and yz also in L, or xz is not in L and yz is not in L. So what is here? If you have the two x and y, and you have the string z, and once you have concatenated, then xz, this string is in the language, and yz is also in the language. And here xz, if either this condition is true or xz is not in the language, then yz also is not in the language. In this situation, you can say that x and y are not distinguishable. But remember, in this case, for distinguishing, one string is sufficient. If you can identify one such string z, which is from the sigma star, for which you can say one is in the language and other is not in the language, then you can conclude that x and y are distinguishable. But for the case of indistinguishability, you have to test for all possible z which is taken from the sigma star. Means if for every string z that belongs to the sigma star, means you have for every z belongs to the sigma star. If you find that xz is in the language and yz also in the language, or xz is not in the language and yz also not in the language, and for every such string z, means you are not knowing any string z which is taken from the sigma star for which you can say one is in the language and other is not in the language. So you can say that in this way the string x and y are indistinguishable. If x and y are indistinguishable, then your fs should not go for the different places. This is our requirement. So why it is so? You can simply see that if x and y are not distinguishable, then it should not go for the different places. It should go to one places on receiving the string x and y. And from that state, if you are getting the string z, then you will have, you can go either final state, means which is if it is going to the final state means exit is in the language, or it is not going to the final state, it means exit is not in the language. So that's why in order to find out the states which are equivalent, actually we need to identify which are the strings in the sigma star which can be distinguished. If you are able to distinguish, then on receiving such strings your fa must go to the different places. And if you are not able to distinguish, then you can say that your fa should go to only one place. Actually, what we are actually trying to identify, if you have the two situation, no? You have the strings in the sigma star, you know, we have the strings which is in the sigma star. You have the sigma star. This is the bigger set. You have all possible strings in this set. So if you have all possible strings, maybe infinite strings, so your fa can receive all such possible strings. And if all such possible strings are distinguishable, this means what? Your fa should go to the different places. If it goes to the different places, this means that your fa should have the infinite states. And it means you can't construct the fa for such cases. If you are not able to, if you don't have the finite strings that you can distinguish, then you cannot construct the fa. If you find that there are infinite strings which are the distinguishable, this means for every such strings you have to go to the different places. You need to remember. So that's why we try to identify that among the strings in the sigma star, which are the distinguishable and which are non-distinguishable. If the strings are distinguishable, then for such strings, on receiving the strings, your fa goes to the different places. Like you have two strings, y and x, right? If you have two string y and x, which is taken from the sigma star, so if you start from the q0, and we assume that we have the machine which is set up, you have the set of states and you have the input symbols. This is the initial state and final state is a and transitions. Okay, we assume like this. So q0 is initial state. So if you start from the initial state, x is taken from the sigma star, and you find that this is equal to delta star q0 y. What do you mean by this? We have seen the transition for the delta star yesterday. And what delta star says, if delta star says that whenever you are in some state, and in that state you are receiving the substring, say for example x. So from that state, where your automata can go. So output of this is what? You have some state. Okay. So output is some state, say for example p. Here you are saying that you are in the state q0 and you are receiving the string y. And if you are saying that delta star q0x is delta star q0y. This means if this is the p, then this is also p. So both are same state. So what happened? If you have the situation like this, if you have the two strings y and x which is taken from the sigma star, such that if this condition meet, the condition is that delta star q0x starting from the initial state, for the input x, input string x, you are going to the state p. Means you have the initial state q0, you have, and for the string x, you are going to the state p. And from the initial state q0 for the string y, you are also going to the same state. Okay. So this is for the case of y. You are also going to the same place. Then what I'm saying that then x and sorry x and y are indistinguishable. So you cannot distinguish in why it is so. What is the condition for indistinguishability? If the string x and y are indistinguishable, this means if you take some string z from the sigma star, which is taken from the sigma star, for all z from which is taken from the sigma star, if you have xz, xz and yz, if x and y are not distinguishable, then xz you will have two situations. Either xz belongs to the language and yz also belongs to the language, or xz not in the language and yz also not in the language. So both are in the language or both are not in the language. So this lemma, actually this is the lemma. This lemma says that if you have the strings x and y for which if you find that delta star q0x and delta star q0y is remain same, it means states are same, then x and y are indistinguishable. Why it is so? Because for both these strings you are going to the state p, x and y, and from the state p, if you can take any z from the sigma star, any z from sigma star, then your fa goes to some state. Say for example q dash, it goes to the q dash. Now q dash either final state or q dash may not be the final state. If it is the final state, then xz is in the language and yz also in the language. And if q dash is not a final state, then xz is not in the language and yz also in the not in the language. So this lemma says that if you start from the initial state q0 and for the two strings, if you are going for the same place, and then we know that from if you are at this state p and for any strings that you can take from the sigma star, your fa will go to some state, and if your fa goes to some state, then there will be two conditions: either the state is final or the state is not final. So either both in the language or both it will not be in the language. So you can say that x and y are indistinguishable. Okay. So this is actually you need to know in the same, once you are given the language, then first you need to identify actually, but this is the difficult task. What are the strings in the set sigma star for which you can distinguish with respect to L? We are distinguishing with respect to the language, given language. And this is very simple. It is not very difficult. You don't want to go for complex one. Simply you have two strings x and y, and both are from the sigma star. We are interested for finding that whether x and y can be distinguished or not. If x and y are distinguishable, then you will have some set which is also taken from the sigma star. So exactly one will be in the language and other will not be in the language. So if one string is sufficient to distinguish, if you have find at least one such string for which you can say that xz is in the language and yz is not in the language, or xz not in the language and yz is in the language. So either you find this situation or you can find this situation. So if you have this situation, if you can identify at least one such z which is taken from the sigma star, okay, you don't require to find all possible z. You just at least you should have one z for which you can say that xz is in the language and yz not in the language, or xz not in the language, then yz in the language. So x and y are distinguishable. We can distinguish x and y. If you are going to distinguish x and y, then how you can distinguish with respect to the fa? You can distinguish x and y if and only if you can go to the different places. Means you can go to the different state. So your fa must go to the different state if you are going to distinguish. If x and y you are not going to distinguish, then you don't require to go to the different places. So you need to identify the strings for which you can go to the different place and for which you can go to the same places. We define the relation like IL. This is the relation which I say that indistinguishability relation with respect to the language L. We are going to distinguish with respect to the L. So we have two strings x and y, say x and y, which is taken from the sigma star. X is related with y, means you have the string x and you have the string y. We say that the string x and y is in this relation. What is the relation? IL. IL is indistinguishability relation. Means x and y are related in this kind of relation. So when you can say that x and y are in this relation, if and only if for any z which is taken from the sigma star, either xz and yz, okay, both are in L, or xz and yz both are not in L. You can similarly means you say that x is related with y in this relation IL. This means x and y are not distinguishable. So you cannot distinguish the strings x and y. So you can say that you can easily identify that the relation IL, this is the equivalence relation. Why it is? What is the condition of equivalence relation? It must be the reflexive. Okay. It must be reflexive, and it should be symmetry also, and it should be it should have the transitivity relationship. You should have the transitivity. So you have the situation actually. You are saying that x is related with y. So if x is related with y, the reflexivity, in the case of the reflexivity, you can easily say that x can be related with x in the relationship IL. This means x and x you cannot distinguish. So this is the reflexive. Similarly, y and y you cannot distinguish. In case of the symmetry, if you are not going to distinguish x and y, then you are also, this is also remains same. You are not going to distinguish. So y x is related with IL, x and y are related with IL, then y and x also related with IL in this relation. This is the symmetry cases. In case of the transitivity, we have the situation if x IL is x is related with y and y is related with, say for example, z. This means what? X and y cannot be distinguished, and y and z cannot be distinguished. This means, this implies that x and z also in the relationship. So this is the transitivity. That's why actually ILB will say that this is the equivalence relations. And for the case of the equivalence relation, we have the very important theorem, which is known as the Myhill Nerode theorem. With the help of this theorem, with the help of Myhill Nerode theorem, you can easily prove that whether the given language is regular or not. So now you have the three situations. If somebody gives you the language L and asks you to prove whether it is L is regular or not, if you have the question for the regular, whether the language L is regular or not, then there are three ways to prove that we have discussed here. One is you can try to construct the grammar for the language. And if you have the regular grammar, then you can say that L is regular. Other way to prove whether L is regular is to go for the regular expression. If you can construct the regular expression for the given language, then you can say yes, the language is regular. Third one is if you can find that the equivalence classes are finite. If you find that equivalence classes are finite, then what you mean by this? If equivalence classes are finite, means there are finite set class of strings for which you can find you have the finite number of classes. This means you have the finite number of states. One class corresponds to the one state. So one class of strings, for one class of strings, your FA goes to one place. For other class of strings, your FA goes to the different state. And if number of equivalence classes are finite, this means you must have you have the finite states. And with the help of the finite number of states, you are able to construct the finite automaton. So actually having the finite equivalence class which is finite, this means you have the FA. This says that you have the finite automaton. If you have the finite automaton, then you can say that as FA is the device for accepting the regular language, and hence the given language is regular. So this Myhill Nerode theorem plays important role for you. So see, you can see some example like this. If you have some language, like you have the language 0 and 1 and n is greater than or equal to 0. So now you may think that can you construct the FA for this language? Yes, there is FA for this language. So if you want to construct the FA for this language, this means what? Your FA must have the finite number of states, and this means you must have the finite number of equivalence classes. So how would you know this FA has the finite number of equivalence classes? This means you need to identify the classes of strings which you can distinguish. So what are the number of classes, equivalence classes you have? So you can easily see that for corresponds to this language, you have the language L. Okay. So for the language, with respect to the language L, you want to find out some string. Say one X you may take. X can be O raised to power I, and Y can be taken as Y is OZ. Now this is from the sigma star, and Y is also from the sigma star, because here you have the alpha weight. Alpha weight contains 0, 1. So sigma star contains all possible strings. So string of zeros. So X is taken from the sigma star, and Y is also taken from the sigma star. And I and Z are different. You can have anything. Now if you say that the strings X and Y are distinguishable, then you must find some Z for which you can say one string X, one of the strings, exactly one of the strings XZ and YZ are in the language. So say if you have taken some Z, like Z is 1 raised to power I, you have this situation. So what happened? XZ, and you have the two string XZ and YZ. So XZ is what? XZ becomes 0i and 1i, means same number of 0 and same number of 1. Here in case of the YZ, j whose 0j and 1 I. This means j number of zeros and I number of ones. And see, it is clear that this is not in the language where this is in the language. Now I and j can be anything. I and j can be anything 1, 2, 3, 4, 5, 6, 7. So you, you find that there are infinite possible strings for which you can distinguish. If means every two strings x and y are distinguishable because I and j can be anything. And if this is the situation, this means you have the infinite number of equivalence classes. Infinite strings you have which are distinguishable, and for remembering all such strings, your FA must go to the different states. And this means if you want to construct the FA with the minimum with finite number of state, for this language it is not possible to construct the FA in finite number of states because you need to remember the more number of infinite number of equivalence classes. And hence you can say that the language L, which is 0 and 1 n, is not regular. Is not regular. And this is the Myhill Nerode theorem, says that if the language is regular, then you must have the number of equivalence classes finite. And you see that in these cases, you will find that the number of equivalence classes are not finite here because every two strings x and y are distinguishable with respect to some z. So you conclude that L is not regular. This is also one way to prove using the Myhill Nerode theorem whether the language is regular or not.